All right, so you know how we always thought we had supernovae, like, all figured out? Well, turns out there might be some, like, cosmic plot twists we didn't see coming.
Oh.
Yeah, so we're going to be diving deep into this article from scitechdaily.com today.
Yeah.
It's called Cracks in the Cosmos, the Flawed Physics of Massive Stars and Supernovae. And it's all about how this little thing called Iron 60 is throwing a wrench into everything we thought we knew about these giant star explosions.
Oh, it's like finding a clue at a crime scene that totally changes the case.
Exactly. But before we get to the mystery, let's set the stage, right?
Okay.
We know that massive stars, they create elements as they burn.
Right.
And one of those is iron 60,
Yeah.
which then gets flung out into space when the star goes supernova. And the cool thing is we can actually detect the gamma rays from that decaying iron 60 here on Earth.
Yeah, it's like a cosmic fingerprint. Gives us clues about supernovae that happened like ages ago. And so we use these fingerprints to build models of how stars live and die.
Like a giant cosmic puzzle.
Exactly. Yeah, it's putting all those pieces together.
But here's where things get really interesting.
Okay.
Researchers at Michigan State University and FRIB, they found something strange. The amount of iron 60 that we are detecting, it doesn't actually match up with what our models predict.
Huh. So it's like we're missing a piece of the puzzle.
Yeah, it's like we're missing a piece of the puzzle.
Right.
And this is where those cracks in the cosmos come in.
Yeah.
To understand why this mismatch is such a big deal, you have to know that studying iron 60 directly is incredibly tricky.
Oh, I see.
The problem is its precursor, iron 59, it's incredibly unstable. It decays so fast, it's like trying to study a melting ice cube.
Wow.
So how did they even figure this out if iron 59 is such a slippery character?
Well, they came up with a pretty ingenious workaround.
Oh.
Yeah, they developed a new technique called the beta-Oslo method. And essentially, instead of trying to study the unstable iron 59 directly, they used a process called beta decay to create it indirectly, which then let them study the iron 60.
So they kind of created a backdoor to study this elusive iron 60.
Exactly, yeah. They found a way to get in.
And what they found through this backdoor was a total game changer, right?
Absolutely.
Yeah.
Yeah. Their findings suggest that stars are churning out way more iron 60 than we originally thought, possibly double the amount.
Wait, double? That's not just tweaking our model a little bit. That's like a major overhaul.
Yeah.
What does that mean for our understanding of these supernovae?
Well, it means our models are missing something big. Think of it like this. Like if you're baking a cake and it keeps coming out flat.
Oh, okay.
Maybe you need to adjust the amount of baking powder or something.
Right.
But if you find out you've been using salt instead of sugar all along, that's a fundamental problem. This iron 60 discrepancy, it's like finding out we've been using the wrong ingredient in our supernova recipe this whole time.
Oh, okay. Now that is a seriously flawed cake or supernova. So what are some of the main ingredients that we might need to re-examine? I mean, where do we even begin to fix this?
Well, one of the biggest question marks is the role of stellar rotation.
Okay.
We know stars spin.
Right.
But we may have underestimated how that spin affects everything, from the way a star mixes material in its core to how it eventually explodes.
So it's not just about how fast a star is spinning. It's about how that spin affects the entire life cycle of the star, right down to its explosive grand finale.
Exactly. It's like, think of a figure skater.
Okay.
Their spin affects every jump and move that they make. We need to understand the figure skating physics of stars much better to get this supernova recipe right.
So you're saying our models might need a serious upgrade to account for these cosmic pirouettes.
Exactly.
This is getting pretty mind-blowing. What else are we missing?
Another big one is the mass limit for stars to go supernova. We've always thought that stars needed to be a certain size to explode. But now...
Hold on. Are you saying that we've been wrong about which stars have the right stuff to go supernova?
Yeah.
That some stars we thought were too small might actually be packing enough punch?
Precisely. That's exactly what this research is suggesting.
Yeah,
it's possible that some stars we thought were destined to just kind of fade away quietly, they might actually go out with a bang.
Whoa, that would totally shake things up. And wouldn't that also mean that there are more supernovae happening than we even realize?
It's definitely a possibility. And if that's the case, it could mean that certain elements are more, those created in these explosions are more common in the universe than we thought.
So this isn't just about tweaking our understanding of supernova. This is about rethinking the cosmic recipe book, like how much of each element exists in the universe.
Precisely, yeah.
Yeah.
It's highlighting just how interconnected everything is in the cosmos, you know?
Yeah.
You can't just change one ingredient without affecting the whole recipe.
Right. And speaking of ingredients, you mentioned the beta-Oslo method earlier. It sounds like this new technique isn't just a one-hit wonder. Could it help us solve other cosmic mysteries too?
Absolutely, yeah. Think of it like a new scientific instrument, like a more powerful telescope or a faster spaceship. The beta-Oslo method could help us study other rare isotopes that are difficult to produce and observe, giving us a clearer picture of what's happening inside stars.
So we're not just rewriting the recipe book, we're also getting new tools to read it with. What kind of mysteries could this method help us solve?
Well, one exciting area is understanding the origin of the elements themselves. Each element has its own unique origin story, and many of them were forged in the fiery hearts of stars. The beta-Oslo method could give us new insights into how those processes work.
That's incredible. It's like we're tracing the lineage of the atoms that make up everything around us, even ourselves.
Mm-hmm.
Okay, before we get too lost in the cosmos, let's bring this back down to Earth for a moment. How does this all connect to us here on our little blue planet?
That's a great question. You know, it's easy to think of supernovae as these distant, abstract events, but they're actually intimately tied to our existence.
Yeah.
Remember those elements that are created in supernovae?
Yeah.
They eventually make their way into new stars, new planets, even life itself.
Hold on, are you saying that the iron in our blood and the calcium in our bones, they were literally forged in these massive star explosions?
It really is, yeah.
That's pretty mind-blowing.
It's a reminder that we are all connected to the cosmos.
Yeah.
So these grand cycles of creation and destruction. We're literally made of stardust.
Wow, talk about a family history. So this research isn't just about understanding distant stars, it's about understanding where we came from.
Exactly. It's about connecting the dots between those distant cosmic events and our own existence here on Earth.
You know, I think what fascinates me most about this is that it's not just about finding answers, it's about realizing how much we still don't know. Like, this whole Iron 60 thing has basically thrown this giant question mark into the cosmos.
Yeah. That's the beauty of science, isn't it? It's a constant process of discovery and revision. Every new finding opens up these new avenues to explore. It's like exploring a vast, uncharted territory. We're always pushing the boundaries of our knowledge.
And this Iron 60 discovery feels like we just stumbled onto a whole new continent. We thought we had the map figured out, and now it's like, wait, there's a whole landmass we didn't even know existed.
A perfect analogy. And who knows what else we'll find as we continue to explore, you know? This discovery has definitely thrown a wrench in our understanding of supernovae, and it's forcing us to re-examine some of our most fundamental assumptions. But that's what makes it so exciting.
Right. It's like the universe is saying, think you got me figured out, think again. So where do we go from here? What are the next steps in this cosmic detective story?
Well, first, we need to refine our models. We need to figure out how to incorporate this new understanding of Iron 60 production and what it means for things like stellar rotation and mass limits.
It's like we need to go back to the drawing board, or maybe even get a bigger drawing board. What kind of research will help us fill in these gaps?
Well, one area is to look for more evidence of these missing supernovae, the ones from stars we previously thought couldn't explode.
So more cosmic detective work, looking for clues in the form of those Iron 60 fingerprints.
Exactly. We also need to continue developing and refining techniques like the beta-Oslo method to study other rare isotopes and gain a more complete picture of stellar processes.
It feels like we've stumbled onto a whole new chapter in the story of the universe.
Yeah.
And it all started with this tiny atom, Iron 60.
It just goes to show that sometimes, the smallest things can reveal the biggest secrets.
Right.
And this discovery has certainly opened up a whole new world of questions and possibilities.
It makes you realize how much there still is to discover out there.
Yeah.
Even in something as seemingly well-studied as supernovae, it's like we just scratched the surface and found this whole hidden layer underneath.
Exactly, yeah.
So, okay, before we wrap up this cosmic deep dive, let's try to zoom out a bit. I think we've covered a lot of ground here. From flawed models to new research techniques to even our own connection to the cosmos. What would you say are the biggest takeaways from all of this?
Well, I think one of the key things to remember is that science is a process. It's about constantly questioning and testing and refining our understanding of the world around us.
Yeah.
This Iron 60 discovery is a a perfect example of that. It's challenged our assumptions and forced us to rethink what we thought we knew about supernovae.
Yeah, it's like we thought we had the universe all figured out, and then it throws us a curveball like, nope, not so fast.
Right.
There's still plenty of mystery left to unravel.
And that's the beauty of it, isn't it?
Yeah.
There's always something new to discover, something to keep us curious and engaged. This research has opened up a whole new set of questions about supernovae, about the origins of elements, about our place in the cosmos. And those questions will drive further exploration and discovery for years to come.
It's almost like this Iron 60 discovery is like a gift of more questions, more mysteries to ponder. And I think that's a pretty awesome gift to receive.
I couldn't agree more. It's a gift that keeps on giving,
Yeah.
inspiring us to keep exploring and pushing the boundaries of what we know.
So to all you listeners out there, the next time you look up at the night sky, remember those twinkling stars might hold the secrets to some of the universe's biggest mysteries. And who knows, maybe you'll be the one to help unravel them someday. Keep that curiosity burning, keep exploring, and never stop wondering about this vast and incredible universe we call home.